need mathematical expectation to be able to do our project that's coming up, where you create a game, you calculate the probability and the expected value for your game, and then we play all the games and we see if that was true. So expected value is notated E of X. Capital E is for expected value. And what it does is it represents the long run average of like winning and losing, the value to the player. So, if I go to the casino and I play a game, like sometimes I'm going to be winning, so I'm going to get money. And sometimes I'm going to be losing, so the casino's going to be taking my money. And what this expected value is if I recorded like when I won $5 and I lost $1, and when I won $100 and when I lost $1 20 times, if I recorded all those things and then added up all those outcomes, like I spent all day at the casino, I added up all those outcomes and divided by how many times I played that same game, that's the average like win or loss to me. Most likely you would expect if I spent all day at the casino that my long run average would be negative, right? If I'm spending all day at the casino, I'm probably not generally leaving with a positive amount of money, okay? And that's because the games are designed as such, right? When you say quit while you're ahead, they mean that because the long run average is you come out in the negatives. Come on, Austin. Yeah. Okay, so here's what you need to know about expected value. Okay, you're going to be creating something called probability distributions. And when it asks for probability distribution, that's like creating the chart. So the distribution is kind of like your chart, just like so you can get used to that. In the chart, you have two rows. The top row is the value. Okay? And when I talk about value, I mean the value to the player. So oftentimes, like we're going to be thinking about a lot of like casino games and betting games where we put down a wager. So like I come up to the game with $1. Okay, I put my wager down. It's not like I'm paying the casino at that moment. That wager just like sits there until the game is finalized. Okay? And sometimes what might happen is I win, so I take my wager back, which is like me leaving with what I came with, and then the casino also pays me money. Right? So then I leave with like some positive amount. Maybe I'll win $1. Okay, so I'm leaving with a +1. Or I win $5, so I leave with a +5. The dollar that I wagered doesn't count as a plus to me because that was what I came with. Okay, it's just the amount that the casino pays me. Okay. In other scenarios, I might wager that $1 and then the game gets played and I break even. Like the casino doesn't take my $1, I don't get any money from the casino, I just take my wager back and walk away. So it's as if I had never played the game. Okay, so then the value to me as a player right there is 0. I didn't win anything, and I didn't lose anything. In other cases, obviously I'm going to lose. So I put my wager down $1, and then when I lose, the casino takes $1. So I'm walking away from that table without the $1 I came with. So I'm like -1 for my value. So the values you put into the probability distribution are like, are you leaving with what you came with? Are you leaving with more than what you came with? Are you leaving with less than what you came with? So it can be positive, negatives, and zeros. Probabilities are like for each of those values, each of those different outcomes, what's the probability that that actually happens? What's the probability that I walk away with $1 or $5? What's the probability that I walk away with 0? Okay, I break even. Or what's the probability that the casino takes my $1? I walk away -1. Okay, so you have to calculate all those probabilities. And this is where, in those bottom row, you're going to be using all the things that we've been doing the last few days, right? Do you need to create a sample space? Do you need to just count things? Do you need to do combinations? Do you need to do permutations? How are you going to find the probabilities? Okay. Okay, and then this is very subtle in your notes, so you might want to like highlight, underline, box. This is the calculation, or like you can think about it like a formula for expected value. So if I say like what is the expected value, then you got to do this calculation. So basically what you do after you create this probability distribution is you take the value for each outcome, multiply it by that probability, and then add that up with the other values multiplied by their probabilities. So it's just the sum of the products of values multiplied by probability. Okay, and then these things are just, remember, values are just the things that are happening to me, the player. You got to think about how much money you're leaving with compared to what you came with. And then the probabilities of each outcome are your different P's. We'll do the first example together, and then I'll let you kind of like work through the second example, and I'll kind of like add things up as you work. Okay, this is roulette. So we had a question on our homework the other day about roulette, but just to review, there are 38 slots, 1 through 36, and then 0 and 00. Half of the slots from 1 to 36 are red, and half of those are black. Both of the 0 and 00s are green. Okay, this is what you're going to be doing on game day. You're going to place a simple $1 bet on the game. Okay, and in this case, we're doing a $1 bet on red. Okay, you're not going to be betting $1 on game day. You'll bet a Tootsie. Tootsie Rolls. But you can only bet one. You can't be like some high roller and wager all your Tootsies. No. Okay, so we're going to make the $1 bet on red. If a ball then lands in the red spot, we get the dollar back. So that's our wager, right? And that's not me winning. That's just like my wager is not taken by the casino. And I get an extra $1. So they have to pay me because I won if it lands on red. If it lands on any other different color, which those different colors are black and green, then they take my wager. They take my $1. So I'm walking away with one less dollar than I came with. Okay, let's state the sample space. So you're going to want to do this on your projects. Okay, sample space. Depending on what your bet is what your sample space is. So my bet was a $1 bet on red. Therefore, my sample space should be all the colors on the roulette wheel. So that would be red, black, and green.
I'm stupid.
That's my squiggle bracket for sample space. What is the probability of winning? Okay, so I'm going to write out the probability of winning. And then in context of this problem, remember my bet was on red, so that's the probability of red. Okay. And let's see, there were half of 1 through 36 that were red, so that would be 18 is the favorable outcomes for that, so I can just count that. And then the total outcomes possible are 38. So simplify that, that's what? 9 over 19. Okay, probability of winning. And then what is the probability of losing? You can do losing a couple of different ways in this problem, right? Like you can think about losing as not being on the reds. So that could be like the complement, 1 minus the probability of reds, 1 minus the probability of winning. Those are the only two outcomes that are possible. Or you could say that losing is the same as the probability of landing on black or green, right? And so then you add up the black, 18, plus the green. That's 20 over 38, which is 10 over 38. Oh, sorry, 10 over 19. Apologies. And again, like I said, you could have done the complement on that one. 1 minus 9 over 19 would be 10 over 19. So there's lots of different ways for you to calculate probabilities. Okay. Create a probability distribution for the outcomes of the game. So I'm going to have those two rows, value and probability. When it asks for probability distribution, remember it's asking for the chart. A distribution is like what could actually happen. I'm going to list all the outcomes and all the values to me as a player. Okay, well, I have two probabilities. 9 over 19, that's my probability of winning. And 10 over 19, that's the probability of losing. What are the values to me, the player, when I win? I get an extra $1. Okay, remember, I do put my wager down, but I'm not paying it. It's like, I don't have my wager, the casino doesn't have my wager, it's just sitting there. It's wagered. When I win, I take my wager. That's not a win, because I had that before I came to the table, right? And then the casino pays me $1. So what am I really walking away with that I didn't have before? $1. Okay, so the value to me is $1. You don't count the wager as a win because you didn't pay to play. Like the casino didn't take it away from you. Okay, it just sat there. And then what happens when you lose the value? They take that $1 that's wagered. Then they're actually taking it away from you and you are minus $1. Okay, now I should have mentioned this on the last slide, but you know, I'm pretty well convinced because there's like two options on this roulette for me that like I either land on red or I don't land on red. Like there are only two ways for me to win or lose. You can always check your probabilities, like if they're like seeming to be correct. The probability line should always add to 1. So like 9 over 19 plus 10 over 19, that adds to 1. That's 100% of the things that can happen in the scenario. Okay. Back here on that previous slide, these probabilities always add to 1. And that'll be really helpful for some people on their games. Like, did you really calculate all the possible outcomes that exist? If your probabilities are less than 1, you're probably missing something. If your probability is over 1, you're overcounting something. So you might have to like find an overlap. So that's kind of a nice way for you to double check that that's all good and well. Okay, last two problems really quickly. What is the mathematical expectation? So this is actually making the calculation. Okay. And we're always going to assume starting off that we're making wagers of 1. So we're going to do E of x equals. And we use our probability distribution. You just take the value times the probability. 1 times 9 over 19 plus negative 1 times 10 over 19. That's 9 19ths minus 10 19ths, so negative 1 19. Since I'm talking about dollars, I might like to see that in dollars and cents. So 1 divided by 19 is, it rounds to like 0.05. So that's like negative 0.05. Okay, so that's a long run average of all my wins and losses. Sometimes I won, sometimes I lost. In the end, it's going to average out. I add them all up and divide by the number of times I played. It's going to average out to be negative 0.05. If I play the game 100 times, how much money would I expect to win or lose? You just take the number of times you played the game times your expected value. So that would be 100 times negative 0.05. So I would expect to lose $5. All this negative stuff, this is for me, the player, right? I I'm expected to lose basically a nickel over the long run course of this game. And if I play 100 times, that would really come out to be like $5. What's the expected value for the house? Plus 0.05. The expected value for the player and the house are just opposites of each other. What the player loses, the house gains. So if I play that game 100 times and I'm losing $5, the house is getting $5. Now stop and think about a casino. Every game at a casino is going to have an expected value that is negative. So that the player, long run average, is paying money to the casino, right? I mean, you can go to the casino and you can win. Okay? But long run average, as that game gets played over and over and over again, the house is making money. Okay, can you read through the next scenario and try to set it up, and I'll kind of like interject and fill in things in a little bit. Note that this one, your probability distribution is going to have more than 2 probabilities because there's more than one way to win in this game. What do you think? Would you consider it winning? No. Would you consider losing? No, I would call it breaking even. So breaking even is not winning or losing. Agreed. Breaking even. Yeah? No, I would say the sample space would be the outcomes that are possible in the end. Yeah, the number of dollars. 1, 5, 10, 20. Those are the outcomes you get. Okay, sample space would be the outcomes possible from the envelopes. Those are your $1, $5, $10, and $20 bills. For the probability of winning, you have to think about which outcomes are considered wins. 10 or 20, right? I wouldn't consider a $5 envelope a win because it's like I'm walking away with the same stuff I had. That doesn't feel like really exciting to me at all. Okay. So there's 110 and 120, so that would be 2 out of 10 or 1/5. Okay. Probability of losing, that would be the probability of pulling a $1, which are there 6 of them? Okay, so that would be 3/5. Now here's where things change. When you create that probability distribution with the values and the probability, you're not necessarily using these 2 probabilities. You may or you may not. It depends on the setup and the values to the player. Okay, so what I like to do is I like to think about my sample space. If I pull the $1 envelope, what is the value to me, the player? -4. I put my wager down, which was $5, and I only got $1 back, so I'm walking away with -$4. In the next one in my sample space is a $5 bill. What's the value to me, the player? $0. If I pull the $10, I'll have a $5 win, and if I pull the 20, that would be so nice. I'll have the $15. You can see that'd be tempting. You might just grab the $20 bill. That would be great. So we're going to have to, like for the -4, that is the probability of losing, right? 3/5. For breaking even, you'll have to calculate that one. How many $5 bills were in the envelopes? 2, so that's like 2 out of 10 or 1 out of 5 for breaking even. And then while your probability of winning was 2 out of 10 or 1/5, you have 2 different tiers of winning, which some of you are going to have for your games. You might have something that's really hard to do, so if somebody does it, you're going to pay them 2 Tootsies instead of 1 Tootsie. Okay. So you can have a level, a tier. In each of these tiers, there's only one envelope, right? 1 out of 10 and 1 out of 10. So the probability of winning is 2 out of 10 because these are both increased value to the player. Okay. But you have to separate it in the distribution. Mathematical expectation. That's going to be -4 times 3/5 plus 0 times 1/5 plus 5 times 1/10 plus 15 times 1/10. Let's see, I'm going by memory here. Is that -0.4? Brody is agreeing. Okay, so if you type that into the calculator, you get -0.4, which means long run average, I adding up all my outcomes that I did at the game, and that would be like a -0.4. Okay, divide by the number of times I played the game. So if I play this game 100 times, my expected win-loss will be 100 times -0.4, which is that could add up fast, $40, right? And you'd probably believe that too, right? Like most of the time, I'm going to be putting that $5 down and only getting 1 back. So I'm going to be losing 4 quite a bit. Okay, and even when I win 20, if I play 100 times, I'm not bound to pick that 20 lots of times. Okay. Let's see. Before you leave, I just want to help you out, like understanding the back side. So will you flip it over and look at the problems on the back? This is your homework for tonight. There is expected value on the quiz tomorrow. Okay. So there's 5 games. And then it says down at the bottom, for each game described above, answer the questions 1 through 5 or 1 through 6. So that's basically what we did on the front. Like make a sample space, do the probability of winning, do the probability of losing, make the distribution, calculate expected value, and what happens if you play 100 times. Okay, so that doesn't really, the sample space and figuring the probabilities is what's going to take the longest. After you do 5 games, okay, then you answer 7 through 10. So like, what game do you want to play the most? What game would you not play? Think about your reasoning for those things. I just want to help you out really quickly. If you'll watch for number 1, the house rolls a die, and they could roll like a 1, 2, 3, 4, 5, or 6. So to create your sample space, something really nice that works out really well is then to say, because I also roll a die, is to say that if the house rolls a 1, I can roll a 1, 2, 3, 4, 5, or 6. And if the house rolls a 2, I can roll a 1, 2, 3, 4, 5, or 6. And if the house rolls a 3, I can do a 1, 2, 3, 4, 5, or 6. Okay. And if you read that problem, it says when we get the same number, this is a break even. If I get less than the house, that's a win. And if my roll is higher than the house's roll, that's a lose. So it's kind of like using that tree diagram, and that would be an easy way for you to count the number of ways you can win, lose, and break even. Okay.